Today we're going to look at our transformation investigation part 2. So for this first part, it says graph each of the following using different colors and then make conclusions based upon your graphs. So go ahead and do the first problem on your own and pause the video. When you're done, you can unpause the video and we'll check your work. So looking at the first problem, our parent graph is x squared. And so we could, make a table if we want to help us graph this, but we know that 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. And of course, if we do the negative side, negative 1 squared is 1, negative 2 squared is 4, and negative 3 squared is 9. So this gives us our quadratic function, which makes our parabola shape. So that's our parent graph. Now we've done these transformations before. So if you have a 2 on the outside of your equation, notice that means the 2 is not being squared. So what happens when we do that to our graph? That is going to change our graph vertically. So if I go ahead and plug in those values, again, 0 squared is 0. And if we plug in 1, notice that 1 squared is 1, but 1 times 2 would give us a y value of 2. So now you have 1, 2, and negative 1, 2. And if I were to do 2 squared is 4, and 4 times 2 is 8. So now we have 2 and 8. And negative 2 and 8. So notice that from our parent graph, the x values stayed the same, but what changed were the y values. We've stretched them vertically upwards. So for this value went up going that way. Let me use a different color. So this point moved up that way, and this point moved up. So they all moved up. So this is what we call a vertical stretch by a factor of 2. So vertical because your y values are changing. So delta y means a change in the y. So if we look at the next one, if we do 1/2, well, 0 squared times a half is 0. If I plug in 1 squared times a half would give me a half. Same thing with negative 1. If I did 2 squared is 4, and 4 divided by 2 is now 2. Same thing with negative 2. And I could do 3, but since 3 is not an even number, I'm going to do 4 instead because it's going to look better on my graph. So if I did 4 squared we know is 16, and 16 divided by 2 is 8. So we have 4, 8. And negative 4, 8. So this would be my new graph. And notice it's below our parent graph, so that means your y values are vertically moving down from the parent graph, so going this way. I'll draw an arrow, so it'd be essentially going this way. So this is what we call a vertical compression by 1/2. So again, we've changed our y values. So based on our graphs, what can you conclude about that a value being multiplied by your original parent graph function, in this case f of x? And it should say, what does a do to the graph, not c. I forgot to change that value. So we just said that the absolute value of a, when it's bigger than 1, it's again going to be a vertical stretch by a factor of a, so the absolute value of a. And if it's in between 0 and 1, it's a vertical compression by the absolute value of a. Now, why did I use the absolute value? Because remember that if a is less than 0, that's a different transformation. This is a reflection across the x axis. So that's why we're using the absolute value of a. So just to look at a graph that we have right here, so this is the parent graph, and I'm going to move that a value that's in front. So notice that if I move that a value, numbers that are bigger than 1 are vertically stretching. So notice that the x value of that 0.11 stays the same, -1 and 1 are staying the same, but the y values are the values that are changing. So notice that if it's in between 0 and 1, that brings our graph downwards, which is again a vertical compression. And if we have the negative, remember the negative flips it across the x-axis, or excuse me, reflects it across the x-axis. So make sure you're using those mathematical terms, vertically stretching, vertically compressing, reflection, when you're writing your transformations out. So let's look at the next one. The parent graph f of x equals sine of x is shown below. Label the key points on the x and y axis, then graph h of x and g of x on the same grid. Make sure to label your new points. So for this, remember that for the sine of x, remember that we said to find the key points, we can use our b value in the period. So our b value is 1, because that's what's next to the x, and if there's nothing there, it's 1. So remember that we said that it's b times the period is equal to 2 pi. So if the b value is 1, that means the period is equal to 2 pi divided by 1, or just 2 pi. So that's the period of our graph for our parent function. And so remember the key points are going to be the period divided into 4 equal parts. So 2 pi divided by 4 is pi over 2. So we learned that in the last unit. So we can see the key points are the intercepts and the maximums and the minimums. So this is 1 pi over 2. And then the next one would be 2 pi over 2, or pi, 3 pi over 2, I'm going to write it up here. And then 4 pi over 2 is 2 pi. So that gives us our parent graph for sine. So now what happens, and we talked about this in the last unit, but just to revisit it. So now what happens, notice my b value is equal to 1/2. So if my b value is equal to 1/2, then what is happening from our parent graph? So if we find our new values, we know that the period equals 2 pi divided by b. So in this case, 2 pi divided by 1/2 would give us 4 pi, because you are going to multiply by the reciprocal of the denominator, which is 1/2. So that would be 2. So 2 times 2 pi is 4 pi. So that means that the key points are going to be 4 pi divided by 4, divide the period by 4 equal parts. So 4 pi divided by 4 gives us pi for our new key points on our graph for this next function. So if our new key points are pi, so then on my graph we started at 0. The next key point would be pi, which is over here. And so 1 pi, 2 pi would be the next key point. And then 3 pi. So the next key point would be here. So this is 3 pi, which would be at -1, and then 4 pi. So this is my new graph. So notice that even though my b value is 1/2, that our new graph is twice as long as the parent graph. So that's why we call this a horizontal stretch I, and it's 1 over your b value. So in this case, the absolute value of 1 over b would be the absolute value of 1 over 1/2. 1 divided by half is 2. So it's a horizontal stretch by 2 from our parent graph, because it's twice as big as the parent graph. So you could also find your parent graph values by doing 2 times x. So 0 times 2 is 0. 2 times pi over 2 gives us pi. 2 times pi is 2 pi. 2 times 3 pi over 2 would be 3 pi, and 2 times 2 pi would give us 4 pi. Notice that gives our new values. And notice that our y value stayed the same. So 0 stayed 0. Then we had 1, 0, -1, 0, just like our parent graph. So if I were to write out the parent graph table values, we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. So 0, 1, 0, -1, 0. And remember, if you think about your unit circle, just to show you real quick, remember those are the y values on your unit circle here, 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 and here. So it starts at 0, 1, 0, -1, 0. Again, looking at the y values on your unit circle. So for the next one, let's go ahead and look at when our b value is equal to 2. So when our b value is equal to 2, that means the period would be equal to 2 pi divided by 2, which is pi. So now our period is equal to pi, and the key points would be the period divided by 4, so pi over 4. So now we're going to be counting by pi over 4 on our graph. So we have 1 pi over 4, which is right here. And then if it helps remember to write the values above, you can. So this would be 2 pi over 4, which is pi over 2. Then we get 3 pi over 4, and 4 pi over 4 is pi. So for this, if we graph, we have 0, 0. At pi over 4 now it's 1, 0. At 3 pi over 4 would be -1, 0. So this would be my new graph. And notice that from the parent graph, which I'm going to draw in black real quick to make it a little bit thicker. So this is my parent graph. So notice that now this graph sine of 2x is half the size of the parent graph. So that's why we call this one a horizontal compression. By the absolute value of 1 over b. So in this case, 1 divided by 2 is just 1/2. So notice that even though you might think, because the 2 is there, it's a horizontal stretch. Remember that the horizontal movements are going to be opposite thinking. So this is a horizontal compression. So the reason it's a compression is because it's half the parent graph. But notice that if I were to continue this graph that I just drew, that 2 of the graphs fit inside the parent graph. So that's why that b value is a 2 right there, in case you were wondering. So that means you could fit 2 of your new graphs inside the parent graph. And in order to do that, you have to horizontally compress it by half of the parent graph. So let's go ahead and write our conclusions here. So when the absolute value b is greater than 1, that's a horizontal compression. By the absolute value of 1 over b. And when the value's in between 0 and 1, that's a horizontal stretch by the absolute value of 1 over b. And I didn't fill up the table in this other one, so let's go ahead and do that. So now notice that we were doing 1/2 our parent graph values. The y values stayed the same, 0, 1, 0, -1, 0. But our new parent graph values were 1/2 times 0, which is 0. 1/2 times pi over 2 would be pi over 4, because you're doing pi over 2 times 1/2. Multiply straight across, you get pi over 4. 1/2 times pi would be pi over 2. 3 pi over 4, and then pi. So notice that our new points are 0, 0, pi over 4, 1, pi over 2, 0, 3 pi over 4, -1, pi, 0. So notice that our y values stayed the same for both of them, but our x values changed. So we changed the x values when we're doing horizontal movements. And if we go back up here, these were vertical movements which changed the y values, which is going to be important for when we are going to be graphing these without our calculators. We need to know which values that we're changing. So vertical changes the y values, horizontal always changes the x values. So how do I know the difference? So if I look back at number 1 up here, how do I know this is the vertical versus horizontal? So it depends on where your equation is placed. So if my equation for h of x would have instead been parenthesis 2x quantity squared, notice that now the 2 is on the inside attached to x. So this would be a horizontal movement, where when it's on the outside of the square, it is a vertical movement. So this now is a b value of 2, where this was an a value of 2. And if I wanted to do the second one, h of x would be equal to parentheses 1/2 x quantity squared. So this is an a value of 1/2, where this is a b value of 1/2. So this first one, where the b value is 2, remember that means it's going to be a horizontal compression by half. And this second one, where the b value is 1/2, would be a horizontal stretch by 2, opposite thinking. So I just wanted to see what the difference was for horizontal versus vertical. And so let's go ahead and put it all together in this table. So we're going to summarize and describe the transformations happening to the function. So if we have a parent graph, and notice on the inside of the parentheses attached to x is the b, so that means anytime it's on the inside attached to x, it's going to be a horizontal movement. So this one we know is a horizontal compression. So HC, I can write it all out. So horizontal compression, which I always usually write HC for, by the absolute value of 1 over b. And this is a horizontal stretch, HS, by the absolute value of 1 over b. And again, we're using the absolute value because if that b value is negative like the next one, that is a reflection across the y-axis. And so notice that these are all horizontal movements. Horizontal movements, if you think about your graph, horizontal changes the x. They move back and forth on your graph, going this way and this way, so changing the x values. Now, if we look at the next three, notice that the a value is on the outside and the negative is now on the outside, not attached to x. So that's what tells us this is a reflection across the x-axis. The a on the outside, if it's just not a fraction in between 0 and 1, that's going to be a vertical stretch by the absolute value of a, and this would be a vertical compression by the absolute value of a. And notice that these all change your y values, because on our graph, you'd be moving up and down this way. So that's why it's a reflection across the x-axis, because that would change your y values if you reflect across the x. So let's go ahead and take a look at our graphic organizer. So we have this graphic organizer here that kind of puts it all together for us. So this g of x that we have right here, this g of x, just stands for, that's the transformed graph. So the transformed graph of what? The transformed graph of the parent graph, which in this case is f of x, because the f is over here with the transformations. So notice we have the variables a, b, h, and k. So on the inside, notice that those are always the horizontal movements, which are the b and the h. So these are horizontal movements, which is why you see I have the change in x there. And on the outside, the a and the k, those are vertical movements. So make sure to write in each of these different transformations that we have. So we just talked about when a is less than 0, we reflect across the x-axis. When our absolute value of a is bigger than 1, it's a vertical stretch by the absolute value of a. And when it's in between 0 and 1, it's a vertical compression by the absolute value of A. So if you need to pause the video to write these down, go ahead and do so. And then unpause when you're done. For B, we said that if it's less than 0, reflect across the y-axis because that changes your x. So how do you change your x if you reflect across the y-axis? If the absolute value B is bigger than 1, it's a horizontal compression by the absolute value of 1 over B. And if it's in between 0 and 1, it's a horizontal stretch by the absolute value of 1 over B. And then we've already done H and K a lot this year and in Math 1 and 2. So when your H value is greater than 0, you move right. When it's less than 0, move left. So if you have x minus h in the equation, you're moving to the right. X plus h moves to the left because the original equation is always x minus h. So how do you get that plus there? You'd have to plug in a negative h value, right? So if you were to have x minus negative h, that's where you get the plus from, and that's why it's moving to the left. So if you have k greater than 0, you're moving it up, and less than 0 moves down. So plus k up, minus k would be moving down. The parent graph f of x is graphed below. Describe the transformations made to the parent graph, and then graph the new function. So let's go ahead and write down our general equation. So y equals a times f of b times x minus h plus k. So for this, notice the a value is on the outside. So that means that this is an a value of 2. And so when it's an a value of 2, that, remember, is going to be a vertical stretch by 2. And if you need to use your table to help you, so when your a value is bigger than 1, you can see right here, when a is greater than 1, it's a vertical stretch by that value. So in this case, a vertical stretch by 2. So when you are vertically stretching something, that means you are going to be changing your y values. So that means we're going to multiply our y values by 2 and keep the x values the same. So multiply y values by 2, keep x the same. So here I have a y value of 4. So if I multiply that by 2, 4 times 2 gives me 8. So that value is here. The next one, I have a y value of 3. So 3 times 2 is going to give me 6. Then I have a y value of 0. 0 times 2 stays 0, so that point stays there. And here I have a y value of negative 1. So negative 1 times 2 gives me negative 2. And then if you have a ruler, I would use a ruler to connect these points. And that gives me my new graph. So that's a vertical stretch by 2. So notice the y values changed, but I kept the x values the same. So the next one, notice the a value, because it's on the outside, is 1/2. So this is a vertical compression by 1/2. So again, we're changing our y values. So we're going to multiply our y values by 1/2 and keep the x values the same. So here is a y value of 4. So 4 times 1/2, or 4 divided by 2, is 2. Then I have a y value of 3. So 3 times 1/2, or 3 divided by 2, is going to be 1.5, or 3/2. Then we have a y value of 0. So 0 times 1/2, or 0 divided by 2, stays there at 0. And then the next y value I have is negative 1. So negative 1 times 1/2 would be negative 1/2. So notice that the x value stayed the same. The y values changed. So now my graph was vertically compressed by 1/2. So it's half the parent graph. So the next one, notice that 2 is attached to x, so that means I have a b value of 2. So remember, it's opposite thinking when you're looking at your b value. So that means this is going to be a horizontal compression by the 1 over the absolute value b, so by 1/2. So again, look over here. So when our b value is greater than 1, horizontal compression by the absolute value of 1 over b. So for this problem here, we are going to be changing our x values. So multiply x values by 1/2, keep y values the same. So now the y values stay the same. So if this is an x value of negative 2 times a half, or negative 2 divided by 2 gives me 1, so that moves here. Here we have an x value of 0, so that stays on 0. Here we have an x value of 1, so 1 divided by 2, or 1 times a half, would be a half. And I should have said negative on the other side, so sorry. So that would have been negative 2 times a half would be negative 1. And then looking at this last point, we have 3. So that means that 3 times a half, or 3 divided by 2, would be 3 halves, or 1.5. So notice that the y values stayed the same. We just changed our x values. So that's a horizontal compression by half. So looking at the next one, we have 1/3 attached to x, so that's our b value. So b is equal to 1/3. So opposite thinking, that means this is going to be a horizontal stretch by 3. So again, we're changing our x values. So now we're going to multiply our x values by 3, keep y values the same. So if we zoom in here, we have an x value of negative 2. So negative 2 times 3 would be negative 6. So notice that I changed my x value to negative 6, and the y value stayed at 4. Here we have an x value of 0. So 0 times 3 would stay 0. Here we have an x value of 1. So 1 times 3 would be 3, so that moves here. So again, kept the y value the same. The x value is the only thing that moved. And here we have an x value of 3. So 3 times 3 would be 9. So it's going to be slightly off my graph because 9 is over here. So it'd be right there. And then, of course, I would use my ruler to connect the points. So whenever you can always use that straight line in order to connect your dots. So this would be a horizontal stretch by 3. So notice that our b value is 1/3, so that means that you could fit 3 parent graphs inside this new transform graph. So for the next one, we have 2 different things, because notice our a value is equal to negative 2. Well, so if we go back over here to our chart, when a is less than 0, it reflects across the x-axis. And when the absolute value of a is bigger than 1, it's a vertical stretch by that value. So we have 2 different transformations we are doing when our a value is negative and a number other than 1. So again, this is going to reflect across the x-axis, and it's going to be a vertical stretch by 2. So you're going to have 2 graphs on here, and I always like to do the reflections first and then the stretching compressing. So reflection across the x-axis, again, because remember that the a value changes your y values. So I'm just going to count how far away I am. So if this point is negative 2, 4, so it's going to be negative 2, negative 4. And then we have the point 0, 3, so that becomes 0, negative 3. And then this one would stay here, and this is 3, negative 1, so that becomes 3, 1. So notice that all I did was reflect it across the x-axis, so that was our first transformation. And then the next transformations, we're going to change those points and do a vertical stretch by 2. So remember, we're only changing our y values, the x values stay the same. So here we have a y value of negative 4, so negative 4 times 2 would be negative 8, so that becomes negative 2, negative 8. Here we have a y value of negative 1, 2, 3, so negative 3 times 2 gives me negative 6. So now I have this part right here. And then I have a y value of 0, so 0 times 2 would just stay 0. So I'm going to use my ruler to connect those points. And then the next one I have is a y value of 1. So 1 times 2 is 2. So that point would go here. And then I could use my ruler again to connect these points. So now I have reflected the graph across the x-axis, and I did a vertical stretch by 2. So those are two different transformations. So I want to see both graphs. Anytime you're doing your transformations, I want to see each different transformation. So for this last one that we have, our a value, or sorry, that's a b value because it's on the inside. So our b value is equal to -1/2. So again, we're going to have two different transformations. So if you go back to your table over here, so when your b is less than 0, it reflects across the y-axis. And when it's in between 0 and 1, it's a horizontal stretch by the absolute value of 1 over b. So we have two different transformations that we are making to our graph here. So this is going to be changing our x values. So we have reflection across the y-axis and a horizontal stretch by 1 over 1/2, or 1 over -1/2. The absolute value of that would be 1 over 1/2, which is 1 times 2 over 1, which is just 2. So that's where we get the horizontal stretch by 2. So if I reflect this across the x-axis first, we're going to count how far away from the x-axis we are. So we are at -2 and 4, so that becomes +2 and 4. This would stay here. Now we have a point 1, 0, so that becomes -1, 0. And we have the point 3, -1, so that becomes -3 and -1. So that is a reflection across the x-axis. And then if we want to do a horizontal stretch by 2, again, we are changing our x values. The y values would stay the same. So if I have -3 and -1, the x value is -3 for that point right there. So -3 times 2 would be -6. And then the next one would be -1 for our x value right here. So -1 times 2 would give me -2. So that becomes this new line. Then we have an x value of 0. So 0 times 2 would stay 0. And here we have an x value of 2. So 2 times 2 becomes 4. So that point would move over there. So that would be our horizontal stretch by 2. So this next part says, on each graph below, the parent graph h of x is shown. Sketch and label each transformation being made to the parent graph. Remember, the order of transformations is important and no calculator. So for this first one, notice the negatives on the outside. So if the negative's on the outside, take a moment to see if you can figure out what the transformation is. So on the outside, that means it's our a value. So that means a is -1, which means this is going to reflect across the x-axis, which is going to change our y values. So I'm just going to anywhere I have the y values and move it across, or reflect across x. So 1, 2, 3, 1, 2, 3. So that would be a reflection across the y. So the next one, notice the negatives on the inside. So that's our b value is -1. So that is a reflection across the y-axis, which of course changes your x values. So that means these values would stay there. Then we have 1, 2, 3. So 1, 2, 3, and that's at 5. So that would be reflection across the y-axis. The next one, notice that we have an a value and a k value. So you always want to do order of operations, multiplication first, then division. So this would be a is equal to 1/2 and your k is equal to 1. So that means we have a vertical compression by 1/2, and then we're going to move our graph up 1. So vertical compression by half means that we're going to multiply our y values by half. So I'm going to zoom in because it's going to get hard to see. So 1 times 1/2 is 1/2. Then we have 3 times 1/2, which is 1.5, and then 1/2 right here. So that would be the vertical compression by half. Kind of hard to see. And then up 1. So that would go there, up 1 would be here, and then up 1 would be right there. So that would be my final transformation. So the up 1 from the parent graph. Looking at the next one, notice that that 3 is on the inside attached to x, so that tells me that is my h value. So because, remember, in our parent graph, it's always x minus h. To get the 3 to be plus, it has to be an h value that's negative, which tells us that we're moving our graph to the left 3, so changing our x values. So we're just going to count left 3 for each point. So left 1, 2, 3. Left 1, 2, 3, give us that point. Left 1, 2, 3. Left 1, 2, and that will give us our new transform graph. And for this next one, we have this is our b value. So b value is equal to 2. So remember opposite thinking, that means this is a horizontal compression by 1/2. We're changing our x values. So that means anywhere I have an x value, I'm going to divide it by 2. So -1 divided by 2 is 1/2. 1 divided by 2 is 1/2, so that would be half. It's kind of hard to draw on here, but it should be half. Then we have 3 divided by 2 is 1/2, so 3 halves, 1.5. And then 6 would be 3 and 2.5. So our graph would go like that. So that would be a horizontal compression by half. So notice that our new graph, you could fit 2 of them inside the parent graph. That's why your b value is 2. And for this last graph that we have right here, again, that's a b value of 1/2, which means this is a horizontal stretch by 1/2, so by 2. So again, we're changing our x values. So we're going to multiply our x values by 2. So we have an x value of -1. -1 times 2 is 2. And 1 times 2 is 2. So notice that's twice as big as it was. Here we have an x value of 3. So 3 times 2 is 6. So it moves to there. And here is an x value of 5. So 5 times 2 would be 10. And 6 times 2 is 12. So those points move there. So notice that our y values stayed the same. We just changed our x values. So notice that this graph is twice as big as the parent graph. So that means that the parent graph is half the size of this new graph. And again, here are just written down here all the equations that we had written out before with where each of the variables are. And this is the order of operations that we follow when we're doing our transformations. So we always want to do B, H, A, K. And we'll talk about that more when we actually talk about combining our transformations. So that is it for today.